Hook. A fully loaded Boeing 747 shows up on radar from 200 miles away. The F-22 Raptor, a 43,000-pound fighter jet, shows up as something smaller than a metal marble. We're talking a radar cross-section of just 0.0001 square meters. That's roughly the size of a hummingbird. A hummingbird. And nobody can see it coming. Promise. In the next 10 minutes, you're going to find out exactly how that's possible. Not the vague "it's got special paint" answer you got in school. The real engineering. The geometry tricks. The materials that absorb radar waves like a sponge absorbs water. The reason stealth planes look so weird and angular. All of it. By the end, you'll understand something most people, including most adults, never actually figure out. Let's go. Section 1: What radar actually does and why shape is everything. First, you need to understand what radar is actually doing. A radar station fires out radio waves in all directions. Those waves travel at the speed of light. They hit an object. They bounce back. The station detects the return signal. That return signal is called a radar cross-section, or RCS. The bigger the return signal, the easier you are to detect. Simple enough. Now here's where it gets wild. The shape of an aircraft determines where those waves bounce. And most aircraft are terrible at this. A traditional fighter jet from the 1970s, like the F-4 Phantom, has a radar cross-section of about 6 square meters. That's basically a barn door to radar. It reflects energy in every direction. The radar operator lights up like it's Christmas. Stealth engineers figured out that if you angle every single surface very precisely, you can redirect those radar waves away from the source. Not absorb them, redirect them. Think of it like shining a flashlight at a mirror. If the mirror is flat and facing you, the light hits you in the eyes. But tilt it 45 degrees and the light shoots off to the side. You see nothing. That's why stealth planes look so bizarre. Every edge, every panel, every curve or deliberate lack of curve is calculated to bounce radar energy away from the enemy antenna. The F-117 Nighthawk was basically a flying collection of flat panels. It looked like someone designed a plane using nothing but triangles. And that's almost exactly what happened. The engineers broke the entire aircraft into hundreds of flat facets. Each one deflects radar in a very specific direction. None of those directions is back toward the radar dish. The result was an aircraft with an RCS of about 0.025 square meters. That's roughly a golf ball. A plane the size of a small house, looking like a golf ball on radar. Section 2: The invisible paint that isn't really paint. Shape gets you most of the way there. But not all the way. Some radar energy still gets scattered in inconvenient directions. That's where radar absorbent material comes in. People call it stealth paint, but it's way more interesting than that. The original radar absorbent material used on the F-117 was called iron ball paint. It contained tiny iron spheres embedded in a polymer. When radar waves hit those spheres, the energy gets converted into a tiny amount of heat through a process called ferromagnetic hysteresis. The radar wave literally gets turned into warmth and disappears. Gone. It never makes it back to the radar dish. Modern stealth aircraft like the B-2 Spirit bomber use multi-layer composite materials. We're talking specialized carbon fiber structures, honeycomb panels, and radar-absorbent coatings that work across multiple radar frequency bands. Each layer targets a different wavelength. It's like having multiple filters stacked on top of each other, each catching a different size of radar wave. Here's the catch. And this is where it gets really interesting. These materials are incredibly fragile and maintenance-intensive. A B-2 bomber requires over 100 hours of maintenance for every single hour of flight time. One tiny crack in the coating, one misaligned panel edge, one damaged surface seal, and the RCS spikes dramatically. Suddenly you're visible again. But here's the question that should be burning in your brain right now: if the plane is invisible to radar, how does the pilot see where they're going without giving away their own position? Stay with me. Section 3: How stealth aircraft actually navigate without exposing themselves. This is the part most people never think about. If a stealth aircraft turns on its own radar to navigate or target enemies, it broadcasts a signal. That signal can be detected. Suddenly your invisible plane is screaming its location to anyone listening. You've just defeated the entire point. So stealth aircraft use passive systems wherever possible. Instead of sending out radar pulses, they receive information. The F-22 uses a system called the ALR-94 Passive Radar Warning Receiver. It has 30 antennas spread across the airframe. It listens to enemy radar emissions, calculates their position, and builds a picture of the battlefield without transmitting a single watt of energy. The F-35 goes even further with its distributed aperture system. 6 infrared cameras are mounted around the entire fuselage. The pilot wears a helmet that costs over $400,000, more than most houses, and through that helmet, they can look in any direction and see a real-time composite image from those cameras. They can literally look through the floor of the aircraft and see the ground beneath them. The plane becomes transparent. When stealth aircraft do need to use their own radar, they use something called low probability of intercept radar, or LPI radar. Instead of sending out one powerful pulse, LPI radar spreads the signal across a wide range of frequencies at very low power. To anyone listening, it sounds like background noise. Random static. Nothing to worry about. But the onboard computer knows exactly what it sent and can decode the reflections perfectly. The engineering here is staggering. You're essentially hiding a radar system inside a plane that's already hiding from radar. Layers upon layers of deception built into every system simultaneously. Wild fact break. Okay. Stop for a second. Because this fact is almost too ridiculous to believe. During Operation Desert Storm in 1991, F-117 Nighthawks flew just 2.5% of all combat missions. Just 2.5%. But they hit more than 40% of all strategic targets. One aircraft type. 2.5% of the sorties. 40% of the impact. That is the operational power of stealth technology translated into cold hard numbers. Now back to the engineering. Section 4, the human cost of making something invisible. Here's something the spec sheets don't tell you. Stealth aircraft are absolutely brutal to maintain, and the people keeping them flying work in conditions most engineers would find shocking. The B-2 Spirit is hangared in a climate-controlled facility at all times. Not because the military wants to pamper it. Because temperature changes and humidity literally damage the radar-absorbent coating. A single night in rain or high humidity can compromise the surface enough to require days of repair work. When B-2s flew missions from Whiteman Air Force Base in Missouri to Afghanistan and back, a 44-hour round trip, the longest combat missions in history, maintenance crews had to work around the clock between sorties. The coating itself is applied by hand. By actual human hands wearing protective suits. Technicians use templates and specialized tools to get every single panel within tolerance. We're talking about dimensional accuracy measured in thousandths of an inch. Across a plane with a 172-foot wingspan. By hand. Early F-117 pilots also flew exclusively at night for years after the aircraft entered service. Not because it was faster or more fuel efficient at night. Because visually it's still visible. A human eye or an optical sensor could still pick it out during daytime. Stealth doesn't mean invisible to everything. It means invisible to radar specifically. That distinction changed everything about how these missions were planned, flown, and survived. Section 5, the future of stealth and why it's getting scary fast. Here's where things get genuinely unsettling for anyone tracking military technology right now. Radar systems are fighting back. And they're starting to win in some frequencies. Traditional radar operates in high-frequency bands, X-band and Q-band. Stealth aircraft are specifically designed and optimized against those frequencies. But lower-frequency radar VHF and UHF band uses much longer wavelengths. Those longer wavelengths interact differently with stealth surfaces. They can sometimes detect aircraft that higher-frequency radar misses entirely. Russia and China have invested heavily in these low-frequency detection systems. So stealth engineers are fighting back again. Next-generation aircraft like the B-21 Raider and the NGAD Next-Generation Air Dominance platform are designed to counter a much broader radar spectrum. We're also seeing plasma stealth research, where a cloud of ionized gas is generated around the aircraft to absorb radar energy at the molecular level. No special material needed. Just physics. There's also active cancellation being explored. The idea is wild. The aircraft detects incoming radar waves, calculates their exact frequency and phase, then transmits a perfectly opposite wave to cancel it out. Like noise-canceling headphones. But for a 30-ton aircraft. At the speed of sound. The stealth arms race is accelerating. And the next decade is going to rewrite everything we think we know about what detection even means. Conclusion. Let's bring it home. 3 things that should still be messing with your head. Number 1, the F-22 shows up on radar as a hummingbird. A plane you could park in a suburban neighborhood, invisible as a bird. Number 2, stealth isn't just shape and coating, it's passive sensors, LPI radar, and a $400,000 helmet that lets you see through the floor of your aircraft. Number 3, during Desert Storm, 2.5% of missions hit 40% of targets. The geometry of invisibility changed the math of warfare entirely. This stuff isn't science fiction. It's engineering. Real materials, real geometry, real physics all working together to make the impossible happen. And it's evolving faster than most people realize. If your brain is buzzing right now, hit subscribe. Every week we break down engineering that actually matters, explained like a text from a smart friend, not a textbook. Drop a comment below. Do you think stealth technology will be obsolete in 20 years? Let's actually talk about it.